Good morning, students. Our today's topic is Cauchy principal value for the integrals. In the theory of Riemann integration, we assume that the function is bounded and the range of integration that is finite. But for the integration of unbounded functions, or when we have infinite range of integration, in that case we use the concept of improper integrals, and this concept was introduced by Cauchy. So first of all, we define the general value of improper integral of a given function. So let us consider a function f which is unbounded at a point c in the open interval ab, but this function is bounded in the intervals from a to c minus epsilon and the interval c plus eta to b. Here this epsilon and eta, these are arbitrary small positive numbers. So the general value of improper integral of the function f can be defined as the integral of the function f is equal to limit as epsilon and eta approaches to 0 of the integral between the limits a to c minus epsilon of the function f plus integral c plus eta to b of the function. This expression is the limit. If this limit exists, it is called the general value of the improper integral of the function f in the open interval ab. Here these epsilon and eta, they approaches to 0 independently, but sometimes it happens that the limit does not exist when these two approaches to 0 independently of each other, but exists if epsilon and eta are related to each other. In such a case, the limit is called Cauchy principal value. So now we can define the Cauchy principal value, which is denoted by the symbol p of the integral of the function f between the limits a to b, or sometimes we can denote it by the integral a to b. Here we put asterisk sign of the function f. This Cauchy principal value is defined as the limit epsilon approaches to 0 of the integral a to c minus epsilon fsds plus integral c plus epsilon to b of the function f. Here epsilon and eta we have taken as same. So this value, this is called Cauchy principal value. Similarly, we can define the Cauchy principal value for the integrals which have infinite range of integration. So for the integral having the limits of integration infinite, the Cauchy principal value is defined as the limit a approaches to infinity of the integral from minus a to a fs ds. This is called Cauchy principal value for the infinite range of integration. Now next we define some regularity conditions. So the first condition is Holder's condition. Suppose we are given a function which is a function of s. We say that the function satisfies Holder's condition if there exists constants k and alpha. Here alpha is greater than 0 and less than or equal to 1, such that for every pair of points s1 and s2 lying in the interval ab, we have the condition the absolute value of f of s1 minus f of s2 is less than k times the absolute value of s1 minus s2 raised to the power alpha. So if this condition is satisfied, we say that the function satisfies Holder's condition, and this condition is a regularity condition. In particular, if alpha is 1 in this condition will become f of s1 minus f of s2 mod is less than k times mod of s1 minus s2, and then this condition is called Lipschitz condition. Now next we define Holder's condition for a function of more than one variable. For example, if we have the kernel k, kernel is a function of s and t. Here we are having two variables. We say that this kernel is Holder's continuous with respect to the two variables s and t if there exist constants k and alpha. Here alpha is greater than 0 and less than or equal to 1, such that the absolute value of difference of k of s1 t1 and k of s2 t2, that is less than k times s1 minus s2 mod raised to the power alpha plus t1 minus t2 mod raised to the power alpha. So if this condition is satisfied, we say that the kernel is Holder's continuous. Here the points s1 t1 and s2 t2, they lies within the range of integration. Now next we define Cauchy principal value for contour integrals. So let us take this be a closed contour. This can be open also. This is a regular curve. We have denoted it by L. And let us take C be a pole on this contour. Now let us enclose this point C by a small circle having the radius epsilon and center C, and let L epsilon be part of this contour outside this circle. Then for a complex valued function f, which is a function of z is a complex number of this form x plus iota y. So for a complex valued function, if the function is integrable along this curve L epsilon, here epsilon is small positive number, then the limit as epsilon approaches to 0 of the integral of this function f over this contour, this limit if exists, then it is called Cauchy principal value for the contour integrals, and it is denoted by the symbol p, integral of function of f over the contour L, or we can denote it by putting the asterisk sign in the upper limit and in the lower we write L. This is the Cauchy principal value over the contour L of the function f. Now next definition is what is Cauchy type integral. Cauchy type integrals are the integrals of the form f of z is equal to 1 upon 2 pi iota integral g tau divided by tau minus z. This integral is over the regular curve L and the integration is with respect to tau. This type of integral is called Cauchy type integrals. Next there is a result. We will use this result in the next theorem, Poincare-Barton transformation formula. So you will have to keep in mind these results, which are called Plumage formulas. If we have a Holder continuous function g, which is a function of tau, this function is continuous function of a point on a regular closed contour L, and let us take a point z which tends in arbitrary manner either from inside or from outside the contour L to a point T on this contour. Then the integral, this integral that tends to a limit, this integral tends to a limit which we denoted by f plus, and this is given by half of gt plus 1 upon 2 pi iota integral g tau divided by tau minus t d tau, and the negative value f minus, this is denoted by minus half gt plus 1 upon 2 pi iota integral g tau divided by tau minus t d tau. Here, this boundary value, which is denoted by f plus, this relates to the Cauchy principal value inside the contour L, and this boundary value, which is denoted by f minus, this relates to the Cauchy integral value outside the contour L. So these two formulas are known as Plummet's formulas.